Another topic related to refraction is something called total internal reflection. So total internal reflection occurs when light is totally reflected on a surface and no light is actually transmitted. So there's no refracted beam of light. So let's take a look at this repeated picture and then we're going to pull up a Phet simulation. So basically I have light that's starting off in glass and then it's traveling into air, and so it does go into the air at first, but then it reaches a point where all of the light is reflected. And so it's only possible to get total internal reflection. So here's what's called the critical angle, and then I have total internal reflection, any angle of incident beyond that critical angle, and all of the light is reflected. So this total internal reflection is only possible when light originates in a region with a high index of refraction where it's traveling slow, and it enters a region or tries to enter a region with a lower index of refraction where it's traveling at a higher speed. Any angle of incidence that's larger than the critical angle will be totally reflected with no transmission, and that's what's occurring here in this picture. So the light originally passes through and then it reaches the critical angle where it starts to reflect, and then anything beyond that critical angle, all of the light is reflected. Any angles that are incident smaller than the critical angle will have some reflection, but will also have some transmission. So let's take a look at this with the Phet simulation. So I have my Phet simulation set up so that it is water in the top portion, so that light is traveling from the water into the air. And you'll notice that the angle of incidence in the water is always smaller than the angle of refraction in the air because the light is traveling slower in the water. It has the smaller angle. It's traveling faster in the air. It has the bigger angle. So as I start off with my angle 0, the light travels straight through, and as I increase my angle of incidence, the light bends more and more, and eventually it reaches a point, I have to go slow, where the light no longer enters the air. This right here would be my critical angle. So for water into air, my critical angle is, so let's see, it's a little less than 50 degrees so it's probably around 48 degrees is my critical angle. And then as I go beyond that, the light is always reflected. So before I reach my critical angle of around 48 degrees, so right around here, gotta go slow, there we go, the light is always refracted, and then beyond that, all of the light is reflected. And that's total internal reflection. Now, one of the things that's really important to understand is that if I switch these and I make the top air and the bottom water, where light is traveling fast into a region where it's traveling slow, I never have total internal reflection. So I can go all the way out, basically almost to 90. If I hit 90, it's going to disappear just because it's going to go across the surface. But the light is always bent at some angle inside of the water. So I have to go from a region where the light is traveling slow, like glass, into air, or water into air. All right, let's try something a little different here. Let's see. So I'm going to find the critical angle for water into air, and we already know it's right around 48 degrees, something like that. There we go. How does the critical angle change when you change the index of refraction? So what if I make the index of refraction bigger? So right now it's 1.33. Well, let's do it this way. Let's make it smaller. Let's see if I make the index of refraction in the top region smaller, will the light actually go into the second region? And the answer is yes. So I'd have to go further for my critical angle. So the smaller the index of refraction is, or the closer the index of refraction between the region that I'm starting in and the region I'm going in, so now that's 1.32 versus 1, the closer the indices of refraction between those two surfaces are together, the bigger the critical angle is. So if I make it even smaller, so they're even closer together, I have to go even further, right, to reach that critical angle. So now I'm almost at 55, right? Where before I was at about 48. So if I start off up here and I make them both air, well, that's probably not a good way to do it. So I can start off at 1.25 right here. Well, let's do it this way. Let's start off in glass, right? I can determine the critical angle for glass. Let's see, this type of glass. There we go. I have to find it. It's touchy right there. Okay, there we go. So I have a big difference between the indices of refraction. So I'm starting off where I have a high index of refraction. I'm moving into a region with a low index of refraction. There's a pretty big difference between those values. And the critical angle is pretty small. So the critical angle is a little less than 40 degrees here. If I change this to a different type of glass, so now it's 1.5, I realize that now the numbers for my indices of refraction are closer, so the critical angle is now going to be larger, right? So now it's a little bit more than 40, and as of course I make them even closer, I make it water, then the critical angle becomes even larger. It should be close to 1.48 or something like that. All right. So the critical angle is basically the point at which total internal reflection begins to occur, and then any angle larger than that for the incident angle, the light will always be just totally reflected, and none of the refracted angle, or none of the light will be refracted. And at the critical angle, exactly the critical angle, the light, so here is the picture here, so at the critical angle, the light is bent at 90 degrees in the second region. So we could actually use Snell's law, the law of refraction, and see where that critical angle occurs. So we know that in region 1, if I take the index of refraction in region 1 and I multiply by sine of the incident angle, it's going to equal the index of refraction in region 2 times sine of the refracted angle. So in region 1, we're at the critical angle, and in region 2, the refracted light has reached an angle where it can't bend anymore. It has basically bent to 90 degrees. And it turns out that sine of 90 degrees is just 1, so this number is just 1. So if I wanted to figure out what the critical angle is between two regions, I would divide both sides by the index of refraction in region 1, and I get this expression here that sine of the critical angle is just the ratio of the index of refraction in region 2, where the light was bending, compared to the index of refraction in region 1, where it started. Now, the region 1 index of refraction is always larger than region 2. So up here, that index of refraction has to be larger than down here. It's the only way that you get total internal reflection. So we sort of learned this already, that the critical angle depends on the speed of light in the regions that are surrounding the boundary. The larger the difference in the speed of light at the boundary, the larger the difference in the indices of refraction, and the smaller the critical angle will be. So as those indices of refraction become larger and larger, the critical angle will occur more quickly when the light is being incident, and so you'll have a bigger region of angles where total internal reflection will occur. So we found that for glass, the critical angle was a little bit greater than 40. For water, we saw that it was right around 48, and so we've already sort of looked at that, and we can see how those change. Some examples of how we might use total internal reflection: fiber optic cables actually use that, so that when they transmit data with electromagnetic waves, that the electromagnetic waves don't exit the fibers. They're totally reflected down the fiber, and they can reach the destination. So some other examples, if you've ever seen, my son actually has one of these where it has little fiber optic it just has fiber optics in it, and then at the bottom it's stuck into a light, and then you can see the light at the end of all those fiber optics. So we use this for data transmission now, and it's a really great way to allow less signal loss is to use fiber optics. We can also use surfaces to redirect the light. So because of the fact that glass has a critical angle that's less than 45 degrees, if you use a prism that's a 45-degree prism, you can have light come in, strike a surface that's a 45 prism, and then just be redirected, and you don't get any loss of light out of the different surfaces. And then, of course, you could use this as a double reflection and have that light come out. So we've used that in different types of optical instruments.